Sam, Brooke already ate them all.
Gosh, bro.
She said she needed her protein.
That's fine.
That's Brooke for you. Oh man, excuse me.
Okay, that makes sense to me.
Dia, you want to teach? Ali says it makes sense when you do it.
But she read it out.
Here,
When I read it out.
I got all the answers. You can just... Oh goodness. Where is it? Thank you, ma'am. All right, so a sample survey interviews an SRS of 267 college women. Suppose, as is roughly true, that 70% of college women have been on a diet within the past 12 months. What is the probability that 75% or more of the women in the sample have been on a diet? Make sure to check all conditions for normal approximation. So she checked her conditions down here. We have to check that n times p is greater than or equal to 10, which it is. We get 186.9. You also have to check that n times 1 minus p is greater than or equal to 10. That's also true. It's 80.1. And then your mean is your parameter, which is the 70%. And then our standard deviation comes from p times 1 minus p divided by n, and then square rooted, which she simplified out over there. Can I help you? Oh, okay. Annika?
She said she needed some things.
Let's see. Schmissed today. Schmissed yesterday. Good grades. Sorry. There you go. Thank you. So we have our mean, standard deviation. We know we can use a normal curve, and we want to find that 75% or more of the sample have been on a diet. So Dia used 0.75 for the lower bound, big number. There's our mean, there's our standard deviation. We get that answer. She then explained the answer. There is a 3.71% chance that 75% or more of the women in the sample have been on a diet. The only thing that I would ask be added is the actual normal curve picture. So it's normal, We have a mean of 0.7, standard deviation 0.028. I can count. So that's 0.7, that's 0.728. So that'd be a 0.756. 7.784. 68.672. 65.644. I'm not good with mental subtraction. Double check me on these. 0.616. The addition I am fairly confident on. Subtraction, not so much. And then 75% or more, so like Dia put, our lower bound is 0.75, which is, we'll say around there. So there's 0.75 or more, so we're looking at the stuff to the right. So that's the only thing I would add to what Dia did, is the picture of the curve. Questions? Comments? Concerns? Suggestions? General wonderments? No? Alrighty then. So, today we're going to look at sample means and find the mean and standard deviation for that. Tomorrow is review. I don't see you on Thursday. Test Friday. So we're going to look at another, I don't know what it's called, computer thingy. That little, it's not quite as cool as the Reese's Pieces one. Yeah, it's not as cool as the Reese's Pieces one.
Do we get food?
No, you get food next week. Next week we play with Hershey Kisses. And I mean play. We're going to play with them. We're going to throw them and drop them and play. Allie's got a very straight face. She's like, play with your food? No. Yes, we're going to play with our food. All right, so today you get to watch me play with a little computer program. And that computer program is going to simulate this situation. So there's a high school north of Grand Rapids. Sorry. After I taught this to third period yesterday, I thought, ugh, this is not the best example, but we're going to go with it. The distribution of ACT scores for the seniors at that high school is approximately normal with an average ACT score of 16. And that's the part that threw me off. That's not a good ACT score. Like, it should be higher if we're going to go steal their prep curriculum. Anyways. Average ACT score of 16, standard deviation of 5. We send Mr. Barber to go there to learn about the ACT prep curriculum. We ask him to bring us back some data, so we tell him to pick a random sample of 5 students. He's going to find those 5 students, record each of their ACT scores, and find the mean of the sample. So, before I do my computer thingy, what is the population we're looking at? Sam?
Isn't it Grand Rapids kids who have taken the ACT, the seniors?
The seniors. I'm glad you added seniors in there. So, seniors, I'm going to rearrange a little. Seniors who took ACTs from this high school. Now, what information do we know about their ACT scores? Hi, long time no see.
It's only been like a quarter.
I know, but it's very sad. My new 4th period, not quite as good as yours. What information does it tell us about their ACT scores in the paragraph? the average and the standard deviation. So those are our parameters. And what notation do we use for the parameters? Do I use X bar or mu? Mu. So our average, mu, 16. Standard deviation, am I going to use sigma or S sub x? Sigma. Because they're parameters, we use the fancy Greek letters. When it's a statistic, we just go back to normal English letters. All right, what is the sample that we asked Mr. Barber to take?
Random sample of 5 students.
Thank you, ma'am. Random sample of 5 students. So now I'm going to use the computer program to take a random sample of 5 students. And we're going to find our sample mean. And then we're going to see what happens as we take more and more and more and more samples, 5 students. You okay if I switch over? Thanks, Dia. You're like, this is the same thing. I know. Maybe. There we go. All right. Now, let's see if I can zoom in. I can't really zoom in. If I zoom in, then the buttons are below everything, and then you don't get to see it when I click on it. So, sorry, don't get to zoom in. Here is our population distribution. What's the shape of that population? Normal curve, right? Over here it tells us that there's mean of 16, standard deviation of 5. We're going to take a sample of 5 students. So Mr. Barber goes, he talks to them, he gets their 5 ACT scores, and then we have their average down here. And then usually it tells me the average over here. Why didn't it tell me? Usually, let's see, let's try that again. Usually it tells me it. No? What if I click on the 5? Yeah, see now, oh, I know what it did. It did five samples of 5. Okay, let's clear that. Sorry. There's our 5 samples. There's our mean. Looks around 16, right? There's 0, there's 32, and it looks pretty, well, 16's right here. So maybe 15 for the mean, right? So we got our first X bar was 15. And we're going to take another sample of 5. We're going to put the average down here. And then another sample and another sample. But I'm not going to flip back and forth. We should be able to write them without watching me write 15. Okay? I got to press this button. Do you dip them in ranch or ketchup?
Ketchup and sometimes barbecue sauce. If I really
I'm not a fan of ranch. Ranch is...
I know, it's not good with
No.
chicken nuggets.
All right, so we're going to take another sample of 5 students. And this time, now we're up closer to 17. So we're going to put our next X bar down at the bottom is 17. And another sample of 5 students. And we're up around 17 again. 5 more. Ooh. So that's 16, 15, 14, 13, 12, 11. That was a low one. I don't know why we're stealing their ACT prep curriculum. That one was 19. We're going to do another one. And that was 14. So, what do you think's going to happen watching those 5 samples? What do you think's going to happen the more samples we take? Do you think it's going to be centered around 16? Do you think it's going to be below 16, above 16? What do you guys think? Make a prediction. Should be close to 16. Do you think the shape will mirror the parent population? Do you think it'll be normal? You got this, Dia. So we're going to take, let's do 5 more. We're going to do another 5, and another 5, and another 5, and 5 more, and 5 more. And what do you notice is happening to our shape? It's becoming much more normal. What do you also notice over here with the mean? What are we getting close to? It is moving towards 16. So the more samples we take, the more normal our sampling distribution will become, and the lower our bias will be. So the closer we get to the actual parameter. So we're just going to make a little sketch of that on our paper. I know words. I do. No, I'm not sure, Grace. I'm not. All right, so let's see. We have our number line. Oh, we got 16 at the middle. That's got our highest peak there at the middle. And then it's higher on that side. This one's a little lower. That one's just barely shorter. And then there-ish. And then it drops way down. Even further down. Really small one. And then this one is a big drop to that bar. And then that one, and then that one. So it's not perfectly normal, but it's somewhat normal. We had a mean of 15.77, and our standard deviation was 2.78. So the more samples we took, the more normal our sampling distribution became. More normal our sampling distribution indeed came. Now, that was when our population distribution was approximately normal. What do you think happens if we start with a population that is non-normal? If our population distribution was not normal, would the sampling distribution still be normal? Brooks says no. Anybody else want to venture a guess? Dia said, I don't know.
I like Dia's answer. I'm going to change my answer to that.
I liked that you had a firm no.
It makes no sense, you know. But, I mean, maybe it does. I don't know.
All right, well, now we're going to make our population skewed. Ooh, I messed that up. Sorry. No, no. There we go. Normal, not uniform. I need to learn how to click. All right, so it's skewed. Which direction is it skewed? To the right. So, do you think, and notice, because it's skewed right, our mean is now down at 8. And we have a standard deviation of 6.22. So, do you think that when I take samples, that my sampling distribution will be normal? Or do you think it'll be skewed right, skewed left? Just Dia saying, I don't know. You think it'll be skewed right? Okay, let's take 5.
Just hit 10,000.
But that's so boring. Fine, 10,000. What happened? Why is it normal? So it has to do with the sample size. Notice that Mason told me not to choose 5. I don't think he did it on purpose. I think he didn't want to watch me hit 5 a bunch of times. But if our sample size is above 30, then it doesn't matter what the population distribution looks like. If we have a sample size of 30 or more, the sampling distribution will be normal. 30 or more.
Why 30?
They did a bunch of samples and they figured out that 30 was just kind of where things changed. I don't feel like that's a good explanation, but it's okay. If we take a sample of 5 and they did a bunch of samples of 5 and you still had skewness, and then they said, okay, what if we take a sample of 10? And it still had skewness.
So it was
And
just
they
trial
just
and error
kept, yeah,
until 30.
until they got to 30 and they went, oh, look, now it's normal. So as long as we're at 30 or more, we're going to get a normal sampling distribution. So, sampling distribution will be approximately normal, even if the population distribution is not, as long as our sample size is greater than or equal to 30. Will be approximately normal. Even if population distribution is not as long as n is greater than or equal to 30. This is known as the central limit theorem.
I apologize.
You should. How dare you want a sharp pencil to take notes? Which we abbreviate as CLT. What's going to happen to our sampling distribution if we increase the sample size? And what else?
Closer to the
More compact, because what happens to variability? Decreases.
central limit theorem. Okay. Miss Whittle, is
Yes,
there like Quizlets?
I'm sure there is.
Because last night I was working on the homework and I was like, how am I even supposed to like remember these terms?
I'm sure there are Quizlets out there.
I won't be. Never mind. Sorry. I don't know why I said that.
All right. Now, the other thing I noticed when I was teaching this is that below you're supposed to circle the correct answer, but my little slashes where I give you a choice of words didn't show up. So, I'm going to give you guys time to circle the correct answers for the 3 statements below. There's supposed to be a slash between more, less. You're supposed to choose the correct word. Same on number 2. There should have been a slash between more and less. And then on number 3, a slash between increase and decrease. So take a minute, circle what you think are the correct words, more or less, increase, decrease. Scooby-Dooby-Doo, where are you? I need some help from you.
I know it. It's my favorite show when I was little.
Love Scooby-Doo.
The new Scooby-Doo sucks. But the old season was good. What does it mean?
Yes, dear. I agree.
That's how confident she is.
I think it's just beginning worse as the year goes on. Because I just want to give it a grade.
Allie, that's no good. Should be getting better. All right, Brooke. Let's
Yes.
see. Miss, I did it in pen. I'm so confident.
Okay.
Averages are more or less variable than individual values.
I said less.
That is correct.
Me too.
It's fine.
Averages are more or less normal than individual values.
I said more.
I'm sorry, what did you say?
More.
Correctamundo.
Boom.
All right, everybody should get this one. When we increase the sample size,
It decreases
The variability.
thank you. Decrease variability.
Boom.
If you haven't picked up on it, this is like the definition of a true sampling distribution. I've said it multiple times. It's going to be on the test.
Is it on the test?
No. Maggie, the fact that you found that funny is like a little worrisome.
I know it. She's just this little. She's getting it.
All right. So last class, we were focusing on section 7-2 in the book. What did we look at with the Reese's Pieces? What were we looking at?
Peanut butter.
Candy, peanut butter. What
Orange.
What about the
Proportion.
orange? Proportions.
Boom.
Wow.
You're just like awesome.
We were in search of a proportion of the population with a certain characteristic. So we were looking at the orange ones only. The actual proportion of the entire population is that the parameter or the statistic? Comes from the population, so it's the parameter. They both start with P. For proportions, what notation do we use for parameters? P. When we estimated the proportion based on a sample, it was called a, thank you, Mason, a statistic. And what's our statistic when it comes to proportions? I love how it was British, P-hot. And the example we looked at in class was the proportion of orange Reese's Pieces. If I had been thinking, I would have written this in orange, but I didn't.
Oh, that's so sad.
It is sad.
Missed opportunity.
Say that
You can
again,
just
I'm sorry.
highlight it.
Missed opportunity.
I know. Usually I'm really good about the colors. Not so much that time.
Is that AJ Pugliano's name
I,
tag thing?
I don't. Yes, he's the only AJ I have.
Oh, it's okay.
All right, so this section and back here, what were we looking at? Were we looking at proportions?
What are you doing?
Did we look at the proportion for the ACT scores?
Yes.
No, Maggie, no. We looked at means. We looked at the average ACT score.
You looked at me like you wanted me to say yes, so I said.
I just wanted you to pay attention. That was the biggest thing. All right, so
I'm attentive.
in your homework tonight, you're going to be focusing on means. We are in search of the average value and standard deviation of some characteristic within the entire population. So when we look at the actual mean of the entire population, is that the parameter or the statistic? Parameter. Parameter comes from a population. And when we're working with averages, what's the notation for our parameter? Mu.
Mew. Like the kitten.
Yes. The estimate of the mean based on a sample is called a, and the notation there?
X bar.
Thank you, ladies. X bar. Now, it does also say up here that we want to look at standard deviation. And over here, I told you if it's a parameter, we use the fancy Greek letter. So the parameter of standard deviation is sigma. The statistic is S sub x. And the example that we looked at there was the average ACT scores. And of course, it wouldn't be a new type of sampling distribution if I didn't give you some new formulas. Because, you
Thank you so
know,
much, you're so generous.
you're welcome.
Bless up.
All right. So down here, we're going to get our new formulas for the mean and standard deviation of a sample mean. So suppose that x bar is the mean of an SRS of size n drawn from a large population with a mean of mu and a standard deviation of sigma. If the population distribution is approximately normal, the sampling distribution is also approximately normal. If our if our population distribution is not normal, our sampling distribution would be normal as long as our sample size is 30 or greater. So, the mean of the sampling distribution of x bar, after we took a bunch of samples, what happened to our x bar? Did it get close to our parameter? Yes. So, just like the mean of p hat was p, the mean of x bar is mu. It should go to our parameter. So the formula you would see is mu of x bar equals mu. Probably the weirdest formula we write. Mu equals mu.
Oh, I agree. What?
Say that again?
What? Yeah. I just, like, why wouldn't mu equal mu? Yeah. Like,
When we
instead of
take a
sampling
bunch
distribution?
of samples, so our sampling distribution, the mean of our sampling distribution should go to our parameter.
So x bar is mu.
So the mean of our x bar is mu. But the notation we use for mean is mu. So we have the mean of x bar is mu. But it's weird
Why?
because you...
That is also how I feel.
I was just stating.
Look.
Mean of
No, I'm
x bar.
looking.
Here's our sampling district. You're not looking.
I
You're
am
looking at your fingers.
I'm so fascinated.
We took a bunch of samples of the students,
Right.
the ACT scores. We were told they had an average of 16.
Okay.
The more samples we took, the closer our average got to 16.
Oh.
So the average of your sampling distribution approaches your parameter, which is a weird looking formula. The mean of our sampling distribution is our parameter. That's all it says. It just looks weird because we have mu on both sides.
Yeah.
Good?
Okay. Yeah.
All right. Standard deviation. This one I can't make you guys come up with it. I mean, I could ask you to sit and stare at this. How did 5 become 2.78? Anybody want to guess? Huh?
They're
No.
waiting for at some point.
So, standard deviation for your sampling distribution of x bar, you take sigma and you divide by the square root of your sample size. So, the formula would be sigma of x bar, standard deviation of our sampling distribution, is our population standard deviation divided by the square root of our sample size. So focusing on this formula. Standard deviation, is it going to increase or decrease as I increase my sample size? Decrease. If I want to cut my standard deviation in half, what should I do to my sample size? Nope. What's the sample size under? It's under a square root. So, square root of what number would give me 2? Square root of 4. So I would have to quadruple my sample size to cut my standard deviation in half. Because if I quadruple my sample size, I have 4n. And we would square root that. And we know that the square root of 4 is 2. So it would cut my standard deviation in half. So if you want to cut your standard deviation in half, you need to quadruple your sample size. Quadruple. And of course, just like with our other standard deviation formula, we can only use it if the 10% condition is satisfied. And that is that n is less than or equal to 1/10 of n. Your sample is less than 10% of your population.
I have a question.
Yes?
In the homework, it doesn't give you the population, then how do you prove it?
So this one, our sample size is 267. If I multiply both sides by 10, that get rid of the 1/10, right? So I have 2,670. Has to be less than or equal to my population. Well, my population is college women.
Yeah.
Are there more college women than 2,670? Yeah. I don't know the exact number, but I know it's bigger.
Okay.
So I can say it's men.
Okay.
Any other questions? All right, so now that we have those new formulas, we're going to use them in some problems. So the height of all high school not all high school seniors, just North Medford high school seniors, is approximately normal, and it has a mean of 68.8 and a standard deviation of 3.5. Height is measured in inches. So notice that right here, it doesn't specifically tell you what mu and sigma are. You should be able to read that notation and go, oh, that means mu is 68.8 and sigma is 3.5. So we're going to pick a senior from North at random, and we want to find the probability their height is greater than 70 inches. Well, if I'm picking Maggie, my probability is 0. Oh, Maggie's short. It's okay. So, first of all, we're told it's a normal distribution. So we need to draw our normal curve. Some of you lost points on that on the Chapter 6 test because you did a normal CDF question without drawing a normal curve. You can bet on your Chapter 7 test there will be some normal CDF questions. If you don't draw me the curve and label and shake correctly, you're going to lose points. So, mean 68.8, standard deviation of 3.5. .8, 71, 72.3, 75.8, 78.8, so 79.3. And then that'd be 65.3. That'd be 62, 61.8. And then that'd be 58.8, so 57.3. No, 50. Ooh, oh, I hate subtraction. 58.3. Double check me though, because obviously I struggled with that one. What's your question, Dia? All right, so what's the probability that we pick a senior and their height is greater than 70 inches? 70 is in here somewhere. 70. Greater than, going to the right. Normal CDF. Lower bound is 70, upper bound, big number, mean of 68.8, standard deviation of 3.5. And then we put it in the calculator, it spits out a number, and then we write a sentence explaining the number. Did you just say yes for a sentence explaining the number? Usually that's kids' least favorite thing about math. Explain your answer. All right, 70, big number, 68.8, 3.5. So we get 36.59, excuse me, 0.3659. I changed it to a decimal when I read, or a percent when I read it, sorry. Anybody want to try their luck at the sentence? Sam, you do? Why, thank you.
No, I don't think.
Yeah, you don't want to.
I have the right to remain silent.
Are you? I didn't know you were under arrest, but okay. If you cannot afford a lawyer, one will be appointed for you. The 5th, where they plead the 5th.
I just had a test.
What?
I just had a test on that. I was thinking out
I
loud.
don't think that's correct.
Do you know the entirety of the Miranda rights?
I think it's right to kill just like what you get from that.
I had no clue. Sam, I think you got that question wrong.
Oh, I might have.
Yeah. Dia says it's the 6th, and I would believe her over me.
I believe her.
Wait, the right term is silent. It's
The
pleading,
5th,
it's the
yeah.
fifth,
You
yeah.
plead the 5th, you don't incriminate yourself. I don't know.
There's another one you can also do. That's for something different.
Anywho, so Sam doesn't want to try a sentence. He's gonna
Maggie wants to.
remain silent. So Maggie,
Maggie
Sam said you want to. No?
No.
No?
We'll upload it today.
Mason,
What?
a sentence to explain our answer?
Sure. Bad idea. 36.59%. No, don't pick me, honestly.
Clara?
There's a 36.59% chance the randomly chosen senior is taller than 7 inches.
That was beautiful. I'm going to do my best to copy it. There's a 36.59% chance and that a randomly chosen NMHS senior. I was a really wonky end, sorry. NMHS senior is taller than 70 inches. Was anything different about that problem than what we've done in the past? Did we change anything? No? Did we change anything? Was it a normal CDF? A normal. It was. Now is where I'm going to change things. So instead of picking one senior, we pick 10.
Oh, what?
We're going to find the average of their heights, and we want to find the probability that the average of their heights is greater than 70. So this is where those new formulas come into play, because I found a sampling distribution. I took a bunch, well, not a bunch, I took 10 kids and I found their average. So the mean of my sampling distribution should be mu. So I'm still going to use 68.8 here. My standard deviation is the thing that's going to change. So standard deviation of X bar is your population standard deviation divided by the square root of your sample size. What do I need to check though before I can use that formula? The what?
The one thing.
The one thing, yes, that one thing, the 10% condition.
It's like the one thing.
So our sample size was 10. If I multiply both sides by 10 to get rid of the 1/10, hopefully my population is greater than or equal to 100. Anybody know how many seniors there are at North? I know.
A billion. It's like
I know.
It's 300.
No, it's not 400. It's 384.
What?
So basically 400.
384.
There are 384 seniors at North.
Jerry is 137.
All right, so 10% condition is met, so I can use my standard deviation formula. So I'm going to take 3.5 and divide by the square root of 10. .5 divided by the square root of 10 gives us 1.1. Let's go with 1.1. That'll make my mental math simple for me. So, we're going to draw our normal curve The mean is still 68.8, but our standard deviation changed to 1.1. So 68.8, if I add 1.1, it's going to be 69.9. Then it'd be 71, and then 72.1. If I subtract, that's 67.7, 66.6, and 65.5. See why I wanted to not use so many decimals? That made it nice and pretty. All right, so same thing. What's the probability that the average of their heights is greater than 70 inches? So 70 is here-ish somewhere, and greater than is to the right. So still a normal CDF problem. Lower bound still 70, upper bound big number. Mean is still the same. It's the standard deviation that has changed, and now it's 1.1 rather than 3.5. So only thing I'm going to change there is 1.1. And this time we get 0.1377. Bless you. Bless you.
Thank you.
We got 0.1377. All right, who wants to try their luck at the sentence this time? Mason?
There is a 13.77% chance that that the average height of 10 random NHS seniors is greater than 70 inches.
Beautiful. Thank you, sir. All right. Any questions? That is inches. Sorry, my
I just don't
eye.
understand why you would ever need to find the average chance that the average would be more than.
We didn't find the
more than
average
the
chance. We didn't find the average chance.
average. It's just like why?
They do lots of things with statistics.
Will I need this in the future?
What are you going to study?
Business.
Oh, yeah. How do you think they learn to optimize profit and all that stuff? Well, you don't have one on your desk right now, but it is right here.
Draw out the curve.
The y is important. The curve, not so much. That I'm just doing to teach a habit for the AP exam. But yeah, the curve, not so much. You're not going to draw it. Although in business, don't they want you like to be able to make graphics a lot? Yeah. Yeah. The calculator, I'm going to teach you a program in the calculator pretty soon. It draws a normal curve for you and shades it. But if I just showed you that to begin with, you guys wouldn't understand what the calculator was telling you. So, this time we're going to pick 50 seniors, find the average of their heights. We want to find the probability that their heights are greater, their average height, is greater than 70 inches. I think you should be able to do this one on your own, Magdalene Dean Moe.
Peace sign.
He said
Brooke Nicole Richardson.
No. It's Brooklyn. If you're really mad.
Mason Ryder Hill.
Boom.
Samuel Patrick Havens.
How do you remember all this?
Ethan Colin. Colin.
Cullen.
Almost.
I can't say your middle name or your last name correctly. Sorry. Megan Elizabeth Hill, right? Elizabeth? Amber Elizabeth Wick. Ooh, Clara, I can't remember. Ruth, Clara Ruth Butler. You weren't here when I went around and learned everybody's
No,
middle
but it
names.
took you forever when you first had me to learn my first name.
What's your middle name start with?
L.
Grace Lynn Smith.
How do you spell it though? Can you spell it?
Lynnne.
Yes.
Oh man, I can't. Oh, Sherry,
Yes.
because it was one of my mother-in-laws. But it's spelled with a CH.
Yes.
Yes. And I never figured out DJ's middle name. Nor did I ever try to guess Diaz because Allie said it's difficult.
Yeah, you can't get it.
Sam, are you okay?
So
Yeah, I'm not gonna try.
I'm going to chicken nuggets.
Dude, I'm
You
sorry.
didn't bring me chicken.
I know. No.
It's because she's a dingus.
I needed my protein, girl.
How much protein is in chicken?
Yes.
Is the standard deviation 0.49?
Why are you questioning the standard deviation?
Chicken nuggets.
I don't know, because maybe if they calculated it was wrong order or something. Because it's 3.5 divided by the square root of 50, right?
3.5 divided by the square root of 50. Yes.
So theoretically, if I just put that right in the calculator, then
Yeah, it should do it. Yeah.
okay.
Yeah. Nobody wants to call me out on this problem.
On what?
The thing doesn't, we can't figure out the standard deviation because the like n is less than or equal to a tenth of population size is an
Thank you, sir.
Oh.
10% condition is not met.
I can't even do that.
We can't do this problem. I said the sample size was 50. I told you the population of seniors was 384. So we can't use the standard deviation formula because our sample size is bigger than 10% of our population. So to teach you, you need to check your conditions. You must check your conditions. So 10% condition is not met. Means we can't do the standard deviation formula, which means, well, can't do the problem. Tomorrow, review, test, Friday. I believe in you all. It was a